Okay, so thank you. I enjoyed that last talk, and it occurs to me that that might be a possibility for a matrix factorization, sort of as an additional term in the intensity matrix. What I'm going to talk about is matrix factorization and regularization particularly. And one of the advantages of going last is that an awful lot of what I'm going to say has already been briefed anyway, so maybe we can get you out of here by 5. I'm going to talk about probabilistic matrix factorization, where the idea is you have a very large matrix R that's n by m, and you want to approximate that by a matrix M, which is the product of two sort of skinny matrices, P and Q, each of which have k rows, where k is much smaller than m or n. I'm usually going to talk in terms of the single elements of either R or M, M sub U and I use U to stand U and I because those stand for user and item, and that's the notation I'm used to thinking about. So we'll have MUI be the inner product of P sub U and Q sub I. And typically R is going to be sparsely populated in the sense that most of the entries in the matrix are going to be missing. A prime example is the Netflix prize, but there's certainly lots and lots of other examples. In Netflix prize, about 99% of ratings were missing. I don't think I have to convince anybody of the importance of regularization in this audience. So I'll just mention that I think that regularization is especially important when you have a situation where there's a great imbalance in the number of entries in particular rows or columns. So if some rows have many more observations than other rows, or similarly for columns, that makes regularization more important. In a very incomplete survey that I did of matrix factorization papers coming out of Netflix prize and some more recent ones, most of the people who used sort of the model I had on the previous page regularized using the following: a sum of the squared errors in the training data plus a regularization term lambda times the sum of the squared elements of P and Q. On the other hand, there were some authors who had this, but they had separate regularization parameters for P and Q. And to make matters a little bit more complicated, some of those authors then immediately said, but for simplicity, we'll let lambda P equal lambda Q. I have to admit that among the papers that I was a co-author of, I fell into both of those camps. So anyway, lambda is usually selected by some sort of cross-validation. So anyway, this leads us to the first research question, which is, should we actually be using separate lambda P and lambda Q? Do we need separate lambdas? And then a less obvious second research question associated with this, which is, should we perhaps use separate lambdas for each of the k dimensions of P and Q? I couldn't come to this presentation without this workshop without talking about matrix completion with noise, as proposed by Candice and Plan. And here the idea is very similar to what I just reported on rank reduction, but without the explicit factors, the P and Q. In other words, there's no so because of that, there's no pre-specification of the rank of M. Instead, the regularization is applied directly to M using the trace norm or the nuclear norm, which is the sum of the singular values of M. And what Candice and Plan propose is minimizing the trace norm of M subject to a constraint on the sum of squared errors in the training data. And this turns out to be, in a sense, equivalent to the L2 regularization I described for in slide or two before, as long as you can sort of line up the delta on this page with the value of lambda previously, and you also have to be able to align the k, the k on that I was using for the dimension of p and q with the rank of m that they're finding. And so anyway, they do this matrix completion by singular value thresholding. So that leads to another research question, which is sort of, should we use the trace norm for regularization instead of doing it through the P and Q? A third method is sort of going back, is more closely related to the probabilistic matrix factorization, which is Bayesian PMF. And here, there's a little bit more specification of the error term associated with the ratings. So the ratings are equal to inner product of P and Q as before, plus an error term, or the other way of putting it is that the ratings have a normal distribution with mean PU prime QI, and then a variance sigma squared. So this variance is unknown, but is assumed to be constant across the ratings. So in the Bayesian formulation, you don't have sort of explicit regularization, but instead there are priors for these vectors, the PUs and the QIs, and then there are also priors for the hyperparameters associated with sigma squared and the other hyperparameters. And this can be fit by Gibbs sampling. And in this paper, they found substantial reduction in the prediction error relative to the MAP results for probabilistic matrix factorization with L2 regularization. So that leads to another research question, which is, well, does BPMF regularize appropriately? I want to generalize this matrix factorization just a bit to a model which includes an overall grand mean mu plus bias terms associated with each user and item, these A sub u and B sub I. And then we still have the PU transpose QI. Now, in some sense, this isn't really a generalization, because if you just added some columns or rows, I guess it would be rows, to the P and Q, you could actually come up with this model as well without having the bias terms. But as a statistician, I like this form much better, and it just feels more natural to me. And also, I think there's some advantages in terms of both convergence and potentially in terms of getting a better fit. With this model, the regularization is very similar to what I showed you before. This line is simply what we had before with regularization terms for the A's and the B's added to it as well. And just as before, where we could separate out the regularization terms, we could do that here. We could create 4 separate regularization parameters, or perhaps something in between the 1 and the 4. And that leads to a question of, should we use separate lambdas when we have the biases? Should we use separate lambdas for the biases from each other, or for the biases as separated from the factors? So before I try to answer these questions, let me sort of tell you what I'm not going to talk about in this talk. There are quite a few extensions of PMF, a couple of which I mentioned last night that I'm not going to get into. One is combining explicit and implicit feedback. By implicit feedback, we mean not only what your ratings were, but what you rated and what you didn't rate. And then time-varying factors, which I did talk about last night, non-negative matrix factorization, L1 regularization. All of these things could be a talk all on their own. And then also regularization parameters that depend in some sense on user or item sample sizes. I'm also not going to talk about efficiency of the algorithms. That's certainly not my expertise. What I've basically done is simply used Newton's method, one coordinate at a time, and iterated to convergence, because I'm not trying to do early stopping or anything. I'm just trying to evaluate what you get if you do get to convergence. The first result is to convince you that you don't really need separate lambda p and lambda q. And the reason for this is that this m equals pq is terribly under-identified. So for example, it's invariant to multiplying one of the matrices by a constant and dividing the other matrix by that same constant. Or where I have C as a scalar here, you could make C a matrix and it would go through as well, just throwing in a transpose on one of the C's. And because of that, it means that you can vary C without changing that first term in our optimization formula. And therefore, you can focus in on the second part, the lambda p times the Frobenius norm of p, and the lambda q times the same thing for q. And if you do that, you minimize this term with the c shown here, and the minimization ends up being the next line, which only depends upon lambda p and lambda q through their product. And so you only need really one of them, and so it's sufficient to say, well, let's make lambda p equal to lambda q. And for the rest of the talk, I'm going to call it lambda sub pq. The other thing I want to do is try to give a little bit of a Bayesian motivation for L2 regularization. And I'm going to start with the sort of the simplest possible case, and it's one that's almost exactly the same as Larry Brown's first case, where I'm going to assume there's just one item, so R is just an n by 1 vector, and we want to estimate, and our assumption is that each rating is equal to an overall mean A sub 1 plus an error, and we want to estimate that A1. And our assumption is that A1 comes from a normal 0 tau squared, and the errors are normal 0 sigma squared. And if you do this, the posterior mean or the posterior mode for A1 satisfies this first summation. It minimizes this first summation, this first term, the summation, and plus the lambda A sub 1 squared. And so it's like a penalized least squares. In fact, it is a penalized least squares. And the lambda sub A in this case turns out to be equal to the ratio of sigma squared to tau squared. And A sub 1 hat looks very much like what Larry presented in his talk for the similar case, except for the fact that I think his lambda was sort of the inverse of my lambda, which can only confuse things. But anyway, that's fine. But the key point on this slide is that the best lambda is inversely proportional to tau squared. So the more signal you have, the less you should regularize. The smaller the signal in terms of variance of the A's, the more you should regularize. So what are the implications of this last slide? Well, the first is that we should probably allow for separate lambda A's and lambda B's if there's the possibility that tau squared sub A is not equal to tau squared sub B. Similarly, we should allow for not only lambda A being different from lambda B, but almost certainly lambda PQ perhaps being different from those other two lambdas. Things get a little bit more complicated if we're trying to figure out whether we should have distinct lambdas for the different dimensions because of the under-identifiability of P and Q. So I put a question mark there. I think one can make an argument analytically as to why these really you should allow for these to be different, but at least for now, let me just leave that as an open question. But note that the PMF, the way that I described it on the first two slides, the regularization does not allow for separate lambdas. The trace norm doesn't allow for separate lambdas, but Bayesian matrix factorization appears to. So what I want to show you now is results of a real toy simulation experiment, where I was sort of assuming movie ratings or something like that with 2,500 users, 400 items, which would make for 1 million cells, and a quarter of those are observed. And that's split up into training, validation, and test data. I'm going to use the training data to estimate the A's, the B's, the P's, and the Q's from the previous slide. I'm going to use the validation data simply to tune whatever lambdas I'm using in a particular model. And then I'm going to use the test data to give an unbiased evaluation of the mean squared error for the particular model. There's substantial, I designed the matrix, filled in the matrix in such a way as to have a substantial imbalance in the number of cases per row or column, so there's a ratio of about 17 to 1 in terms of the number of items rated by the most prolific user to the least prolific, and a ratio of about 30 to 1 in terms of the number of times that the most rated item is rated compared to the least rated item. The simulation model I use is that the rating for user U and item I is equal to the sum of bias terms for both the user and item, and I separate out the first two factors. So there are going to be two factors, it's two dimensions, and I write those out separately, and then there's an error term on top of that. All of these elements are assumed to be normal with mean 0 and independent of each other, and the variances are shown here. So the biggest variance is associated with item variance, second biggest with user variance, smaller ones with the two factors, with the first factor being 4 times as big as the second factor. The total variance is 1.30. The evaluation is based on the test data, as I mentioned before, and rather than the mean squared error for ratings, since we actually know what the means are, what the mean is that ratings are being drawn from, I evaluate based upon mean squared error in predicting the mean. So the mean squared error that I'm going to show in future slides is an average over the test data. I should have a 1 over n out there or something. It's the average over the test data of the square of the prediction minus the true mean that the rating was drawn from. So there are several limitations. The first and most obvious one is that this is not real data, and it's just a toy example. A second is that there's only one replication that I'm going to show you, so it's I don't have any standard errors associated with anything, and it's possible that some of the results would vary with other replications. So let me start with a model that doesn't have the matrix factorization part in it. On this first slide, we're only going to have the item and user biases, and in fact, in this first line, I don't even have that. I'm just using the grand mean as predictions, and so the mean squared error, in theory, should be 0.30, and it comes out just a little bit less than that. When you do put in the user and item biases without any regularization, so this is just a standard two-way analysis of variance, the mean squared error drops to 0.07. We've explained the amount of variance we've explained is 0.2267. Recall that the item and user, the true item and user variances added up to 0.25. So we've explained about 90% of the biases here. It's pretty good. If we regularize, while constraining lambda A to be equal to lambda B, we get a lambda of 9.32 by using cross-validation, the mean squared error drops by another 0.0034. So a bit of an improvement associated with regularization. Relaxing lambda A equal to lambda B, we get slightly different lambdas, but no improvement in the mean squared error in this particular simulation. And maybe that's not surprising because the two lambdas ended up being pretty close to each other. What happens when we start to put in a factor? On this slide, I'm going to use one factor. Now this first line is just the last line from the slide before. When we now add one factor to the model, while restricting the three lambdas to be equal to each other, the mean squared error drops by another 0.024. This first factor, the theoretical amount of signal in this first factor is 0.04, so we've explained 60% of the variance here. For this particular case, now we have an optimal lambda that's a little bit bigger than it was for A and B, so maybe we think maybe we should allow for separate lambdas for A, B, and PQ. And when we do that, we see that they separate a little bit, but again, the mean squared error doesn't improve any. Finally, here's some results with two factors in the model. So again, the first line is from the previous page. I'm going to add in a second factor, but constrain the PQ1 to be equal to PQ2. So I've got separate factors for each bias, and I've got a separate factor for the matrix factorization, but separate lambda for the matrix factorization, but I'm requiring the same for each dimension. And a little bit surprising, the mean squared error goes up now. It doesn't go up by a lot, but it went up some, and the reason I would argue is that the lambda for the first dimension had to go up from 13.44 to 19.84. So we needed to regularize that second dimension more than optimal, presumably to keep from under-regularizing the third dimension. And in fact, when we allow separate lambdas for the two dimensions, you see that's exactly what happened. The regularization parameter for the first dimension goes back down to 13.4 about. The second dimension has a much larger one, and the mean squared error now goes down. It goes down to 0.0428, which is about 0.0011 less than it had been with one factor in the model. So for this second factor, we're getting only now about 10% of the true variance. Let me quickly show you some results for matrix completion. At least in our testing, it performed quite poorly on raw ratings when we gave it raw ratings, but that's not surprising because it's not really designed to estimate the biases. So what we did was we fed residuals from the PMF, which had taken out the user and item effects. When we did that, the mean squared error dropped to 0.0477. The matrix completion software said that it recovered a rank of 1 as opposed to 2. And this mean squared error is still substantially worse than the range of results we got for PMF when we had at least one factor. For Bayesian matrix factorization, again, it doesn't do real well for with the raw ratings, although it did better than matrix completion. We found it did best when we did some early stopping. But again, since it wasn't designed to estimate biases, we again fed it the residuals from the PMF with the bias terms in it. And when we did that, we got an MSE of 0.0433, which was just a little bit above the best one that I had shown you before from probabilistic matrix factorization with biases. And the BPMF worked best with k equals 2. We tried a variety of values. So anyway, in summary, first of all, there's no need to use separate lambda p and lambda q in this formulation. Secondly, theory suggests that we should, however, use separate lambdas for distinct sets of exchangeable parameters. And so the A's are distinct from the B's, so that suggests different lambdas for different bias terms. It suggests different lambdas for the bias terms versus the factors, and also suggests different lambdas for the individual factors. And our simulation results, although tentative, support this need for the separate lambdas across factors. And Bayesian matrix factorization does that automatically by estimating a covariance matrix, a full covariance matrix. And the probabilistic matrix factorization can be tuned to do this, but as the number of dimensions gets up, it will require a work on getting it to do so efficiently. So anyway, thank you. Yeah, so I didn't sort of really say how I fit things. I sort of fit things sequentially in this, which is I fit the first factor, and then I use that as a starting point for the model with two factors. So in some sense, I was sort of sequentially doing an SVD, and I think that that fits in very well with the notion of what's going on. In trying to fit things simultaneously, I think that might be using the SVD of what you get out sort of at each iteration might be the way to work this.
I just want to make a couple of small closing remarks. The first one might be most important. Somebody lost their baggage claim ticket, number 585. So if you're missing yours, I've got it. And if I leave, I'll leave it with the secretary outside. I also just wanted to take this opportunity to thank our sponsors again. This really would not have been possible without them. And just to remind you, these are who they are. And I think all of them had representatives here at this meeting, and I personally would be really happy if some of the stuff that was discussed at this meeting could help, mitigate some of the root causes of conflict or save some lives. So I really am very grateful for the support that these agencies provided us. I also want to thank the program committee. I think I've been given a lot of undue credit here. Part of what made this meeting so great was the high quality of people who came to present talks or posters or just to listen and contribute ideas. And so I definitely want to acknowledge David Brady, David Dunson, Robert Calderbank, Ingrid Dobeshies, and Mauro Maggioni, who all played a really instrumental role in coordinating the whole workshop and technical program. I also want to acknowledge Laura Peterson, who's the pretty blonde woman ringing the chimes every time we're running late. She works at the Washington Duke Inn and really did the lion's share of the organization and coordinated all the food and made sure everything was laid out and took care of just about everything so that none of us had to. And so she deserves quite a bit of credit for that. So thank you again, everyone, for coming. I was really excited to be part of such a exciting and fun workshop, and hopefully we'll have a chance to do it again someday. Thank you. Bye.